So in this module of trees, we are going to cover different things. Starting with, let me just share my tablet screen. There we go. We will start with going through different definitions and different terminologies. After we are well equipped with these terminologies and words and definitions in our mind, then we will move to discuss what is some of the applications of binary trees. And we will finally discuss the data structure of BST, which is binary search tree. So for both binary trees and binary search tree, we will see if we can discuss some of the operations that we do by using these data structures, some of the cool applications where these data structures could be used in order to see how we can apply those data structures, and basically aware ourselves with different complexities of doing different of applying these data structures in different scenarios. So we'll be doing a lot in this module. So are you ready to get started with this module? Yes, perfect. Okay, so let's first begin with different definitions. And when we are talking about definitions, first thing is defining trees itself, right? What is a tree? So we define graphs, and trees are defined from the subset of graph by applying some of the constraints, additional constraints to what we call as graph. So every tree is definitely a graph, but every graph need not be surely a tree. So there is more to the graph. We apply some constraints to this class of graph, and we call that, okay, if graph have this constraints, then that can be called as a tree. What are these constraints? There are two main important constraints. First is connected, and second is acyclic. So if a graph which is given to you is acyclic, that means it doesn't have any cycles within that graph, and all the nodes of that graph are connected, that means it doesn't have any disconnected cluster or disconnected cluster of nodes or any individual nodes in that graph, then that graph could be called as tree. So here we have three examples. In example A, we see that this graph, which is framed of 5 nodes, has this cycle. Because it has cycle, it is not acyclic, and that's why it's not a tree. In example B, we see that this graph has disconnected cluster of nodes, right? This cluster 1 and cluster 2 are both disconnected from each other. And that's why it's not connected, so that cannot be called a tree. But the example C, you see that it's connected and it doesn't have any cycles, so it is acyclic. And because both these things are true for this could be called as tree. Then let's move further to defining some of the components of our tree structure. Some of the important components, that the terminologies that you might come across when you are dealing with problems with the tree or trying to solve problem using the tree data structures, any component, any subcomponents of tree data structures like binary search tree, binary trees, then you might come across these terminologies frequently. What does these terminologies mean? It is very important to understand and not just memorize them. These are very straightforward terminologies, should be super easy for you to understand them. Root. Now, what is the root of a tree? We see that this is a tree data structure over here. Now, definitely in the trees that we know, the one that looks green and one that looks beautiful and one that gives fruits and flowers and vegetables, this is not an environmental science or a biology class. So that's not the tree that we are talking about. The trees that we are talking about is computer science trees. And unfortunately, from our normal definition of trees, where we see like bushes on the top and then it confines to like a smaller stem, like branches and then stems. So it's like bigger on the top and then it starts becoming smaller and smaller, something like this, right? Every tree we imagine is something like this. The definition of computer science of trees doesn't quite follow that. It's more like inverted. So we invert this and we say whatever is here is the top. That's what we draw it. So whatever is the lastmost thing of the tree, that's the root. That's in every tree of computer science that we draw root at the top, not root at the bottom. So here A is the root of this tree. Then we have a couple of other things like parent, children, siblings, and leaf. Let's look into what each of that means. The parent, as you see that if any child, if any, let's divide this tree into different levels, right? So if you see that level 0, level 1, level 2, level 3, so if you see that any node is being connected to any upper layer, from which upper layer level it's coming from, so the node at the upper level becomes the parent, the node at the lower level becomes the child. So in this case, for the children of A consist of a subset which includes B, C, and D. The parent of B is A. And as you would have already defined by now that the multiple children can have same parent, but a single child, so a parent can have multiple children, but a child cannot have multiple parents. So that also applies into our definition of trees. So B has one and only one parent, which is A. C has one and only one parent. So the parent of C is nothing but A. The parent of D is nothing but A. While children of A can be more than one, so it's a set. In the same way, every node, so even if we go to the lower level, then B can be called as a parent of E and F. C is the parent of G, D is the parent of H. In the same way, I and H are children of F, all that, very straightforward. Siblings. Now, who are your siblings? Somebody who is your brothers, sisters, all those people, right? So siblings are the children with the same parent. So here in this graph, we have I and J are siblings. E and F are siblings, while G and H, they are not siblings because they don't have the same parent, although they're at the same level. So they are just single child, G and H. They don't have any siblings. Finally, the leaf. So leaf is a node in your graph that does not have any children, right? So the last most level of your graph will have leaves. All the nodes, no, need not be the last most. It could be any level. If any node at any level does not have any children, then that's a leaf. So here, this node E is the leaf, J is the leaf, I is the leaf, G is the leaf, and H is the leaf. So the leaf includes of E, I, J, G, H. Did I miss any leaf? No. These all are your leaf nodes. Then we have two other terms called ancestors and descendants. So ancestor of any node is all the nodes that appear on its, as like how you would normally define your ancestors, right? Like your parents, your grandparents, your great grandparents, your great 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 grandparents. Those all are your ancestors. So if we are defining ancestors of I, then that includes the subset F, B, and A. These three are ancestors of I. In the same way, ancestors of J are also the same. Ancestors of G is C and A, and so on and so forth. Descendant is the inverse. So the descendant of A is pretty much everything in this graph, right? Apart from A, everything else is descendant because A is the root. Descendants of B includes E, F, I, J, all these nodes. Descendant of C includes G. Descendant of D includes H. That's how we define descendants. Subtree. Now, any tree could be dissected into different subtrees. What a subtree includes is a couple of vertex, a couple of, I would say, nodes. When we talk about trees, we better call things, we call nodes rather than vertex. When we talk about graphs, we call as vertex, right? Both of them are the same. So a subtree is for, in this whole tree, we can say that we have, this could be called a subtree. This could be called a subtree. This could be called a subtree. So a subtree is all the descendants with all edges connecting them. So a subtree cannot be disconnected unless and until it's a leaf node. The subtree needs to have different nodes, a set of nodes, and the set of edges into them. Further, we can also say that even this is a subtree, right? Even this because this is a leaf node, it individually is a subtree. This is also a subtree, and this is also a subtree. So we can dissect the graph and so on and so forth and identify our own subtrees. Now, every node has multiple, one or more subtrees. Finally, coming to the relation between number of edges and number of vertex in a tree. While, does anybody remember what was the relation between number of edges and number of vertex in a cyclic and acyclic graph? We already looked at that. Well, because graph is a more complex data structure, the relation was a bit complicated. If you don't remember, I do recommend you to go back to the previous module, look at that because you definitely missed something. What is the relation between number of edges and number of vertex in tree with the constraints that we apply to the definition of the tree? Because of these constraints, this definition simplifies. While we were talking about the relation between number of edges and number of vertex in graph, we always use less than equal to, or at max, it can be something like this. But while in a tree, you can exactly say that a tree has number of edges, which is equal to number of vertex minus 1. Then some of the examples of a tree. So for you to be able to apply the concept of trees that you learn here into solving real life problems, then you would need to first relate the real life problem to a data structure. And if that data structure is tree, you would need to know how to relate that to the tree. And then you can apply different algorithms of the tree to solve that problem. So one of the example of where we can relate the tree data structure with different things is an hierarchical structure. Wherever there is an hierarchy, the next impulse is, okay, can it be defined as a tree? Where an organizational structure is a perfect hierarchy. If you are the president or the CEO, then you are the root of the tree of that organization. You have different people working working with your guidance. Those people are managers, sales managers, production manager, personal managers, all the managers. Below managers, we have supervisors. Below supervisors, we can have team leaders. Below team leaders, we can have team members and interns and so on and so forth. So, but this hierarchy of people can be exactly represented as tree over here. And that's what is important, to take a real situation and then relate it with data structure. So if there is a hierarchy that you smell in a real problem, then definitely tree should be on your mind, that okay, can this hierarchy be represented as a tree? Another example of how to relate with the tree data structure is binary expression tree. So this is more of mathematical relation. In mathematics, there are expressions, right? So we can use a tree to represent these expressions. Like this tree could be used to represent an expression where we can solve this expression. What is this expression? Is anybody very quick to solve and already have an answer? Very good. So let's see, what is this expression? We solve usually the expressions from the lowermost level. So it's C minus D, which is this subtree. Then we have that divided by this operation, E, right? So that's now this whole subtree is this expression. This is added, which is this operation over here with another subtree. And what happens in this subtree is nothing but A multiplied by B. So this expression over here could be visualized as a tree, this one. So this is how you can also relate mathematical expressions with trees. Okay, so level, yes, we already kind of defined and used levels. What is a level should be pretty clear. It's nothing but it level, or sometimes we also call this a depth. The level of each node is nothing but the length of the path to that node from the root. So here the level of f is the length of the path, right? So 1 and 2. So the length of the path to this node from the root. We always start the levels from 0. So it could be 0, 1, 2 in this way, or the levels, the root is always at the level 0. The For this G, it is 1, 2, and 3 because the length of the path is 3 from G to A. So that's how we define the level. Now, what's the height of the tree? Height of the tree is nothing but the maximum levels in the tree. So this tree over here in this example has 3 levels, and that's where the height of this tree is 3. Okay, so before we move to binary tree, if you have any questions in these definitions that we looked for the tree itself, then please email those questions to me. If you have any confusions on how do we derive trees from graph, some graph, whether it could be called a tree or not, I'm happy to answer all those questions. No questions are good or bad, questions are always smart. So if you have questions, feel free to send those along my way by email and I'll be happy to answer those things. Okay, so next we'll continue with learning about binary trees. Now that first we define graphs, right? From graphs, we derive definition for trees. Now from trees, we are going to derive definition for binary trees. So we call all trees that satisfies some of the constraints. Then those trees could be called as binary trees. What are these constraints? The constraints we are going to put here is in terms of number of child each node can have. We say that if a tree is following this property where all the nodes in that tree has either 0, 1, or 2 children, then we call that tree as binary search tree. So these all are some of the examples of what trees could be called as binary search tree. Any node that's just a node by itself, it's a leaf, right? And a leaf is perfectly fine to be called as binary search tree because it has 0 children. Something like this, because this node has 1 children and this node has 0 children, it's a binary tree. This node has 2 children, this node 0, this node 0. Yes, still less than 3. That's why it's a binary tree. Now this node has 2 children, right? This node has 2 children. This node has 0 children. Again, every node has less than 3, binary tree. In this graph, all this nodes, so this node has 1 children, this node has 1 children, and this node has 0 children. That's why again it's a binary tree. So all these are binary trees. So the definition of binary tree could also be seen in a recursive fashion. Now let's look at how can we recursively define a binary tree. Because this property of either 0, 1, and 2 child needs to be satisfied by all the nodes. So we can say that if a binary tree T is either a set of empty nodes, right? Or, so either if the set is empty, or this consists of a set which has 3 items. One is the root, the second is the left subtree, and we ensure that this left subtree is a binary tree. So we call it as the left binary tree, and the right subtree of this node of the root, and we ensure that the right subtree is also binary tree. Right binary tree. If any root node has these property, or if any tree has these 3 sets, the root, the left subtree, and the right subtree, where left subtree and right subtree are both binary trees, then we can say that, okay, then T is also a binary tree, right? Now look at this into this figure. So we say that let's take this node. This node has left subtree, that's null, right subtree, that's null, and it has root. If there is nothing, then definitely there's nothing to fall under the definition. This node has again left subtree, that's null, right subtree, that's null, and the root itself. Now when we look over here, this node has left subtree, which has 1 node, but it falls under the definition of binary tree. So this is a binary tree, right? We saw here something like this. This is a binary tree. The right subtree is a binary tree. The left subtree is a binary tree. And this is our root node. Because these 3 are the components in that set T, we can say that, okay, this set T is a binary subtree, binary tree. Now, this binary tree is a subtree for this node, and because this root node also has the left subtree as a binary subtree and the right subtree is a binary tree, that's why we can say that, okay, so now this whole set has the property or the definition that aligns with the definition of binary tree, and that's why the T is a binary tree. So I hope that's clear to all of you that how we are defining this recursive definition, right? The recursion is applied from the innermost level to the outermost level, where the innermost level is nothing but the leaf nodes to the root. And then we keep doing it recursively until we say that, okay, if the whole structure follows this definition in a recursive fashion, then the whole structure can be called as binary tree. So some of the examples of a binary tree, the tree A is a binary tree because as you see, all the nodes apart from leaf nodes all the nodes have 0, 1, or 2 children, right? The leaf nodes have 0 children. Even this tree B is a binary tree because all the nodes have 1 children apart from this leaf node, which has 0 children. Then finally, we have, again, some other terms that you might come across when you are going through some of the problems. And these terms are full binary tree and partially complete binary tree. Now, when do we call a binary tree to be a full binary tree? Is when every node except the leaf node has exactly two children. So let's say if you have something like this is a full binary tree. Something like this is a full binary tree. So every node except just the leaf nodes has exactly two children, then that frames a full binary tree. When do we call something as partially complete binary tree? You have already come across this definition of partially complete binary tree. Where did we see this terminologies? When we were defining heap, correct? So when we were defining heap, that's when we defined, so heap itself is defined as a partially complete binary tree with which can be visualized as an array, right? So whatever we learn for heap, that's exactly what partially complete binary tree looks like. You start filling nodes from your left hand side, right? And then filling nodes from your left hand side, you have all the levels that are filled except the last level, which may or may not be, which can be allowed to be incomplete. So if you have something like this is a partially complete binary tree. It's also can be called as heap. Even this is a partially complete binary tree. So because the last level is incomplete, but all other levels are complete. So that's it. So those are the things that terminologies that we need to know for binary trees. Again, if you have any questions on any of these terminologies that we discussed for binary tree, then please email those questions to me. Next, let's move to binary search trees. So now how do we define binary search trees? Again, same way as we have been doing since the beginning. We took graph, we applied some constraints, we defined trees. We took trees, we applied some constraints, we defined binary trees. Now we'll take binary trees, we are going to apply some more constraints, and we are going to define binary search trees. Well, for binary search trees, the constraints are not applied in terms of number of childs or what in the same way as what we did for binary trees, but rather all the binary trees, we apply the constraints in terms of the value that each node can have. And in terms of how these values, what can be the value that can be stored inside the node, we say if it's good to be a binary search tree or it is not a binary search tree. These constraints, we have two most important constraints which we apply to binary trees to become binary search trees or to be called as binary search trees. The first constraint is everything that lies on the left part of the tree from any node needs to be smaller than whatever the value of that node is. The second constraint is everything that lies on the right part of any node needs to be greater than the value of that node. So if we look at this first example, if we dissect the graph, the tree over here, now everything that's falling on the left part, there is nothing, unfortunately. So if there is nothing, we don't need to worry about. Everything that's falling on the right part is greater than 10, right? 15, 25, 30, 37, 65. Everything is greater than 10. If we dissect the tree over here, again, it applies. Everything on the left, which is 10, is smaller than 15. Everything on the right, which is 25, 30, 37, and 65, that's greater than 15. If we dissect over here, the same thing applies. Dissect over here, the same thing applies here, same thing here, also the same thing. So if you have a tree, if you can do this dissections and if it follows these two properties, then we can call it to be a binary search tree. The value stored in the node needs to follow this property. If a node is just alone by itself, just alone leaf node, then definitely it's also a binary search tree because it has nothing on its left and right. So it's hard. If when there is nothing, you don't need to worry about anything. Then you have the third example where you see that it's a single-sided tree, but still it follows the property, right? You dissect here, you dissect here, here, or here. It follows the same property, these two properties, and that's why even this is a binary search tree. Now that we have defined trees, we have defined binary trees and binary search trees. I want to give you a brief glimpse of how the tree class looks like. So when you are coding and when you are using this tree classes included in your header file zip file, um, this is just a snapshot from that code. So the tree class is called tnode. Every node consists of two things. First is the data element itself, and the second is the left pointer and the right pointer. So every node looks something, can be visualized something like this. So this is the node where it contains the data item. The data item could be the node name, it could be the node value like 43, 57, 9, anything, whatever you want to store as item in that node. It has the left pointer and it has the right pointer. Now this left pointer and right pointer can be used to point to the left child and the right child. So as we see here in this piece of code, we have two public data members, the node value, which in this constructor, we assign the node value as item. So by default, the left pointer is null, the right pointer is null whenever you define any T node, any tree node. You have these two pointers and you have the node value. So whatever item you want to store, right, with that node, you need to assign the define in the definition, you assign the value of that. So it will be storing that item. These are the different values could be stored in the item. So for example, let's say we have the abstract tree model. This is how we usually end up drawing trees when we are discussing in our class or anywhere. But this abstract tree model is actually the tree node model that's something like this over here. So the node A, the value itself is A. It has a left pointer and it has a right pointer. Then the left pointer points to the left child, which is B. So the value of this node is B. By default, we would have left pointer to null, right pointer to null, but then we say that the B has a right child, that's D. So we point the right pointer to D and so on and so forth. So this is how this tree is actually stored in this fashion. Now let's work it out. So let's say that this is the piece of code that's given to you. Can you try to draw the tree? What tree is constructed out of this? We are using this class T node, right? We are using the class T node, and this is the piece of code that's written. So what will be the P and Q? Like what is the abstract tree model of this one? Okay, so we have here in this step, we are declaring the P and Q as two T nodes. We have, and each T node has left pointer and right pointer, right? So we have this P and we have Q as our two T nodes. Then in this step, we say that P is new T node, which is of type int. We are giving type into this and we are storing 8 in its item. So it will store 8 over here. By default, this is null. I'm just representing null by ground. People who are in electrical engineering knows what ground means, but if you don't, then null is just, it's pointing to nothing. So it's difficult to show nothing, which I'm showing by the ground sign. Then in this statement, you have Q, which is where we are also giving value 4 to the item. But apart from that, what we are seeing is the left. This is the item. This is the left pointer. This is your right pointer. So what we are saying is the left pointer of Q is still null, but the right pointer of Q is P. So instead of this pointing to null, this is pointing to P. And that's why this tree structure is nothing but Q. It has no Q, it has no left child. It has P as its right child. This is storing 8, this is storing 4, sorry for that, and this is storing 8. This is your abstract tree model with this small piece of code. Let's draw the abstract tree model for this one. I want you to do this by yourself. This should be pretty straightforward. You know that this is item. This is your left pointer. This is your right pointer. Just keep that in mind. By default, if you don't mention anything, then from the constructor that we saw over here, right? From the constructor, by default, it's null. Okay, so we have this P node, which is storing 20. We have Q node, which is storing 40. And you have R node that is storing 30. The left pointer of R is pointing to Q, and the right pointer of R is null. Then you are saying you are redefining the P node, the root node. So you have the root node, which is storing 10. And you say that, okay, the root node has P as its left pointer and R as its right pointer. So this structure, the abstract tree model, would look like root P R, sorry, right? R is over here, and then R has this left child, which is Q. This is your abstract tree model where each of this is storing some values, 10, 20, R is storing 30, Q is storing 40. So that's it. Next, we will further continue discussing discussing further on different traversal mechanisms for binary trees, and then we will jump into different interesting algorithms about binary search trees.